Why the moon always shows the same side to Earth. Have you noticed that no matter the day or phase of the moon, it always shows the same face? It's as if it's eternally staring at us, motionless. But this is neither a coincidence nor something magical. It's the result of a physical phenomenon that occurs in billions of celestial bodies. This is called synchronous rotation. The moon spins on its own axis at the same time as it orbits the Earth. This movement was gradually forced by Earth's gravity, which created a sort of lock over billions of years. In other words, it does spin, but in sync with its orbital movement. That's why the same side is always visible from here. This process is known as tidal locking, and it happens when a planet's gravity interferes so much with a satellite that it ends up locking its rotation. Earth is also affected by the moon's gravity, but since it's much more massive, the effect is far smaller. The moon, being smaller and lighter, was overpowered by Earth's force. During the first millions of years, the moon spun faster, but Earth's gravity created tidal forces that gradually slowed the moon's rotation. These forces slightly deform the satellite, creating internal tension that dissipates energy. Over time, this internal friction reduced the spin speed. The balance point was reached when the moon's rotation came to take exactly the same time as its orbit around Earth, about 27 days. Since then, this synchronicity keeps the same face turned toward us. This doesn't mean the other side of the moon is dark. It receives sunlight. We just can't see it from Earth here. In fact, it's very different from the visible face. It has many more craters and almost no dark planes. This mystery is also linked to gravitational locking. There is a small oscillation called libration that allows us over time to see a bit more than 50% of the lunar surface. This happens because of the moon's slightly oval orbit, which causes variations in the viewing angle. In the end, we can see about 59% of the total surface at different times of the month. This gravitational locking isn't exclusive to the moon. Many natural satellites in the solar system are locked in the same way with their planets. This shows how the laws of physics tend toward a balance of forces. The more time a body spends orbiting another, the greater the chance they'll synchronize. In practice, if you were living on the moon, you would see Earth always in the same spot in the sky. It might appear bigger or smaller depending on the orbital distance, but it would never move. It's the opposite of our view of the moon, which rises and sets every day due to Earth's rotation. This stable behavior is part of why the moon is so important for life on Earth. Its constant presence helps keep our planet's axial tilt more stable, which directly influences the seasons. The moon, silent in the sky, plays a huge role in the stability of our world. This locking also makes the moon ideal for certain scientific projects. Since one side is always facing deep space and away from Earth's interference, it would be perfect for building telescopes and astronomical observation equipment. It's like a natural platform facing the universe. Behind the simple fact that we always see the same face of the moon lies a complex dance of forces, time, and balance. What seems static in the sky is actually the result of billions of years of movement, gravity, and friction. The moon isn't motionless. It's locked in a perfect rhythm with Earth.
2. The true shape of the moon, not a perfect sphere. When we look at the moon in the sky, it seems like a perfect, smooth, round ball. But that image is just an illusion, caused by distance and sunlight reflected off the surface. The moon is actually deformed, full of craters, mountains, and even slightly flattened. It's neither round nor symmetrical. The moon's true shape is more like a slightly elongated ellipsoid, a bit puffier on one side. This happened due to Earth's gravitational influence. Over time, tidal forces caused by our planet slightly distorted the natural satellite shape. The moon's puffier part is exactly the side facing Earth. This is no coincidence. That deformation was caused during the tidal locking process we mentioned earlier. It's a sort of cosmic scar left by the force Earth exerted on the moon over billions of years. Additionally, the moon's surface is full of impact craters. Since it has no atmosphere to protect or wear down these impacts over time, the marks remain intact for millions, even billions of years. This gives it a highly irregular appearance, full of pits and reliefs. Gravity also influences the moon's overall shape. The moon has areas with higher mass, called mascons, concentrations of mass that affect the local gravitational field. These are located under some of the dark planes, called maria, and cause slight variations in spacecraft orbits. These mascons were discovered when space probes flew over these areas and accelerated slightly, indicating a gravitational anomaly. This shows that the moon's mass distribution is very uneven. Its internal structure is also complex, with crust, mantle, and a small core. Despite all this, the moon's overall shape is still reasonably spherical due to its own gravity. Large enough celestial bodies tend to take on a rounded shape. But this sphere is far from perfect. It's full of deformations, roughness, and density variations. Another curious detail is that the moon is moving away from Earth at about 3.8 centimeters per year. This movement causes subtle changes in its orbit and could, in the long term, alter the gravitational balance between the two bodies. Over time, this could even affect the length of Earth's days. The moon also doesn't have a static terrain. Although it no longer has active volcanoes, it may still have light tectonic activity, which causes small moonquakes. These are weak but show that the moon is still geologically alive to some extent. Its surface is also covered by regolith, a fine dust generated by billions of years of meteorite impacts. This dust is highly abrasive and irregular, making the moon's soil even more rugged. There's no erosion like on Earth, so everything remains preserved with much more clarity. When we look at the moon up close, the image changes completely. The surface reveals surprising details with valleys, mountains up to 5 kilometers high, and craters hundreds of kilometers wide. This visual and structural complexity contrasts with the simple image we have from Earth. The moon may look like a calm and uniform sphere to the naked eye, but its true form is the result of billions of years of impacts, gravitational forces, and internal movements. It's not just a round little satellite in the sky. It's a complex body with geology, history, and a structure far more interesting than it seems. 3. How the phases of the moon really work. You've probably seen the moon change shape throughout the month. One day it's full, then it gets thinner until it becomes a small crescent in the sky. This cycle is known as the phases of the moon. Many people think it's caused by Earth's shadow, but that's a myth. The real explanation is even more fascinating. The moon's phases are caused by how sunlight hits it as it orbits Earth. At each position in its orbit, a different part of the lunar surface is illuminated. And since we see this light from different angles, it appears to change shape from Earth's point of view. At new moon, it's between Earth and the Sun. The illuminated side is facing away from us, so we barely see anything. At full moon, it's on the opposite side of Earth from the Sun, and the whole visible face is lit up. In the intermediate phases, we see only parts of it illuminated. This cycle lasts about 29.5 days and is called a synodic month. It's different from the sidereal month, 27.3 days, which measures how long it takes the moon to make a full orbit around Earth relative to the stars. The synodic month is based on the moon's position relative to the Sun and Earth. The full cycle includes the following phases: new, waxing crescent, first quarter, waxing gibbous, full, waning gibbous, last quarter, and waning crescent. These names describe how much of the moon is lit and on which side. This cycle is so regular that it was used to measure time in many ancient cultures. The common mistake of thinking the phases come from Earth's shadow probably comes from confusion with eclipses. In lunar eclipses, yes, Earth's shadow covers the moon, but that only happens at specific times when the sun, Earth, and moon align perfectly. In normal phases, it's just a matter of light and position. Another important factor is that the moon is tilted in relation to Earth's orbit. This tilt is what prevents eclipses from occurring at every full or new moon. For an eclipse to happen, everything needs to align on the same plane, which is relatively rare throughout the year. The waxing moon always appears in the early evening, while the waning moon appears more in the early morning. This happens because of the position it occupies in the sky during each phase. Each change in the lunar cycle alters the time the moon rises and sets, which ancient people also used to track time. The moon's phases also influence natural phenomena on Earth, like tides. During full and new moons, its gravity aligns with the sun's, increasing tidal forces. These are the so-called spring tides. During quarter phases, the forces partially cancel out, creating weaker tides. Culturally, the moon's phases influenced calendars, religious rituals, and even farming. Some people believed certain lunar moments brought more fertility, creativity, or danger. Today we know they're just phases, but the cultural impact is still strong in many parts of the world. Watching the moon's phases slowly change in the sky is a reminder that we are in a constantly moving system. Nothing is still, not even the seemingly motionless satellite above our heads. And understanding this cycle connects us to a more natural, ancient, and deeply cosmic way of counting time. Behind the smooth and familiar shapes of the moon lies a precise mechanism based on orbits, light, and gravity. Each phase we see has a clear explanation, but no less impressive. What seems like a simple change in shape in the sky is actually the reflection of an age-old dance between Earth, moon, and sun. The supermoon phenomenon explained by the elliptical orbit. Sometimes the moon looks unusually big and bright in the night sky, almost like it's closer to Earth. People often call it a supermoon, and it's a moment that captures attention worldwide. But what's really going on here? Why does the moon sometimes seem so much larger than usual? The answer lies in the shape of the moon's orbit. Unlike a perfect circle, the moon's orbit around Earth is slightly elliptical, more like a stretched oval. That means there are times when the moon is closer to Earth, called perigee, and times when it's farther away, apogee. A supermoon happens at perigee during a full moon. When the moon is at perigee, it's about 356,000 kilometers away. At apogee, it stretches to around 406,000 kilometers. That 50,000-kilometer difference is enough to make the moon appear up to 14% larger and 30% brighter in the sky. Our eyes aren't always great at judging this, but the change is real. A full moon that happens right at or near perigee is what we call a supermoon. It's not an official astronomical term, but it's widely used now. The brightness and size difference are more noticeable when the moon is near the horizon. A trick of perspective enhances the effect. That's why it feels so dramatic. The moon doesn't suddenly become more powerful during a supermoon, but its gravitational pull does get slightly stronger. This can lead to slightly higher tides, known as perigean spring tides. It's a small difference, just a few centimeters higher, but enough to be measured and predicted. Interestingly, we can also have a micromoon, when the full moon occurs near apogee. Then the moon looks slightly smaller and dimmer. Most people wouldn't notice the difference without a comparison, but when you see a supermoon and a micromoon side by side in photos, it's striking. The elliptical orbit of the moon is caused by gravitational influences, especially from the Earth and the Sun. It wobbles slightly over time, so the exact timing of supermoons varies each year. We can predict them precisely, though, because the moon's orbit is well studied and mapped. Because of this orbital motion, we sometimes get more than one supermoon in a single year. Occasionally, there can even be two in one month, with the second one called a blue moon, though that's more about timing than color. It's a rare overlap that gets a lot of public attention. Supermoons also have cultural and emotional effects. Some people say they feel more energized or even emotional during one. While science doesn't support major psychological changes caused by the moon, the visual impact is real and powerful enough to stir imagination and emotion. It's also a favorite moment for photographers and sky watchers. The moon rises large and golden, reflecting sunlight across oceans, cities, and deserts. Though it's the same moon as always, that moment of proximity connects people to the sky in a more visceral way, like the universe is suddenly closer. Behind the beauty, though, is a stable, predictable mechanism. The elliptical orbit isn't unusual. Many moons and planets have them. The supermoon is simply a result of geometry and light. But like many things in science, knowing the cause doesn't make it less magical. When we see a supermoon, we're not just witnessing a celestial event, we're watching a dynamic interaction of gravity, motion, and light perfected over billions of years. That glowing disk in the sky is a reminder that even simple beauty can be rooted in deep, elegant physics. The origin of the moon, the giant impact theory. Where did the moon come from? It's one of the oldest and most important questions in planetary science. For a long time, scientists weren't sure. Many theories tried to explain it. But today, one idea stands out as the most likely: the giant impact hypothesis. According to this theory, the moon was formed from a collision between the young Earth and a Mars-sized object named Theia. This event happened about 4.5 billion years ago, shortly after the Earth itself had formed. The impact was catastrophic, but it didn't destroy Earth. Instead, it reshaped it. Theia slammed into Earth at a sharp angle, throwing a massive amount of debris into space. That debris formed a ring around our planet, made of rock and vaporized material. Over time, gravity pulled it together, and the moon was born. It started as a molten sphere before cooling into the moon we know. Evidence for this theory comes from the composition of moon rocks. Samples brought back from Apollo missions show that the moon and Earth have nearly identical oxygen isotopes. That suggests the moon came from Earth's outer layers, not captured from elsewhere, as some older theories claimed. The moon also lacks large amounts of iron in its core. That makes sense if it came from Earth's crust and mantle, which are less dense than the core. Theia likely contributed to the moon's makeup too, but most of it probably merged into Earth or was lost in space after the impact. Computer simulations support the idea. They show that a collision of this scale could produce the moon we see today, both in size and orbit. It also explains why Earth rotates the way it does, and why the moon's orbit is tilted. The impact reshaped both bodies in deep, lasting ways. This wasn't just a crash. It was a creative act of cosmic violence. The impact changed the Earth's axis, helping to create seasons. It may have even stripped Earth of a thick early atmosphere, giving rise to a more stable climate over time. Without the moon, Earth might be a very different place. Some theories tried to tweak the details. Maybe Theia wasn't Mars-sized, or maybe multiple impacts were involved. Others proposed the moon formed from a vapor disk rather than solid debris. But all versions agree, a massive collision played a key role in the moon's creation. Interestingly, we've never found a piece of Theia floating in space. That's probably because it either became part of Earth or the Moon, or was destroyed entirely. Traces of it might exist deep in Earth's mantle, waiting to be discovered in future studies. The impact theory also explains why the Earth-Moon system is so unique. No other planet in our solar system has a moon so large compared to its size. This deep connection between Earth and its moon is rare and possibly essential for life as we know it. Our moon stabilizes Earth's tilt, affects tides, and might have even helped protect early life by reducing extreme climate swings. So while the impact that created it was violent, its outcome made Earth more habitable. Out of destruction came balance. Understanding the moon's origin isn't just about the past. It tells us how planets grow, how systems evolve, and how chaos leads to stability. It's a story written in rock, orbit, and motion, and one of the best clues we have to understanding our place in the cosmos. The far side of the moon and why it's so different. People often talk about the dark side of the moon, but that's not quite right. All sides of the moon get sunlight. There's no side that stays permanently dark. What people really mean is the far side, the hemisphere that never faces Earth. And it's a very strange place. The far side of the moon wasn't seen by humans until 1959, when the Soviet Luna 3 probe sent back the first blurry images. It looked shockingly different from the familiar near side. Instead of wide, dark plains, it was covered in craters, with barely any of the smooth regions we call Maria. Why is that? One reason is the moon's crust. The far side has a thicker crust than the near side, which makes it harder for lava to break through and create Maria. On the near side, volcanic activity in the past created those dark, flat regions, but on the far side, the lava stayed trapped below. Another reason might be tied to the moon's formation. Some scientists believe that after the moon formed, one side cooled slower than the other. The near side, facing Earth, may have absorbed more heat and stayed geologically active longer. That could have led to the asymmetric surface we see today. The near side also has strange gravitational features, like mascons, massive concentrations of dense material. These don't exist in the same way on the far side. The differences between the two hemispheres are so pronounced that scientists still debate exactly why they formed that way. Even the magnetic fields are different. While weak overall, the moon's magnetic anomalies are mostly found on the far side. One theory suggests that asteroid impacts and surface composition differences played a role. Another points to the core and how heat was transferred early in the moon's history. The far side is also radio silent. It's completely shielded from Earth signals. That makes it an ideal location for radio telescopes. Scientists have long dreamed of building observatories there to detect signals from the early universe without interference from human technology. In 2019, China's Chang'e 4 mission became the first to land a rover on the far side. It carried a lander and a small rover named U-22, which is still exploring the region. This was a huge milestone in lunar exploration, opening up a part of the moon we've barely studied. Samples from the far side would help scientists understand its unique geology. Until now, we've only sampled rocks from the near side. Comparing materials could reveal secrets about how the moon cooled, what its interior looks like, and even how Earth's early history unfolded. Living or working on the far side poses challenges. Since it never faces Earth, communication requires relay satellites. But that same isolation also offers opportunities, a perfect place to escape Earth's noise, both literally and scientifically. It's a laboratory of silence. The far side is not dark, it's just distant. But in that distance lies mystery. Its face, scarred by time, holds untouched clues about the Moon's violent past. It reminds us that even familiar worlds can have hidden sides, ones we've barely begun to explore. The Moon is not just a simple rock in the sky. It's a complex, asymmetric body with a history written on both sides, and the far side, quiet, battered, and strange, may hold the final answers to how the Moon, and maybe even Earth, came to be. Lunar gravity. Why it's only 1/6 of Earth's. Have you ever seen astronauts hopping around on the Moon like they're in slow motion? That's not just for fun, it's because the Moon's gravity is much weaker than Earth's. In fact, it's only about 1/6 as strong. But why is that? What makes gravity so different between the two worlds? Gravity depends mainly on two things: mass and size. Earth is much more massive than the Moon, about 81 times heavier. It also has a larger radius. Because of this, Earth can pull objects more strongly toward its center. The Moon, being smaller and lighter, creates a much gentler pull. The surface gravity of the Moon is about 1.62 meters per second squared. On Earth, it's 9.81. That's why someone who weighs 60 kilograms on Earth would weigh only 10 kilograms on the Moon. The person doesn't actually lose mass, it's the force of gravity that changes based on the celestial body. The Moon's lower gravity has some interesting effects. For one, it allows astronauts to move more easily, jump higher, and carry heavy equipment with less effort. It also affects how dust settles, how projectiles move, and even how the human body responds over time. If you were to drop a hammer and a feather on the Moon, they would fall at the same rate. And in fact, that experiment was done during Apollo 15. Without air resistance, the only force acting on objects is gravity. On the Moon, everything falls slower but at the same speed, regardless of mass. Building structures on the Moon might be easier thanks to this weaker gravity. Materials wouldn't need to support as much weight, and heavy loads would be easier to move. However, launching rockets from the Moon also becomes more energy efficient, which could be key for future missions to Mars. But there's a downside too. The human body is adapted to Earth's gravity. In lower gravity, muscles and bones weaken over time. That's a concern for long-term Moon missions. Astronauts would need regular exercise and medical monitoring to stay healthy in such an environment. Gravity also influences how an atmosphere is held. The Moon's gravity isn't strong enough to keep a thick atmosphere like Earth's. That's one reason why it's airless and exposed to radiation and meteor impacts. Its surface is unprotected, which makes it more hazardous for human activity. Over time, the Moon's low gravity has helped preserve its landscape. With no atmosphere, no erosion, and no weather, features like craters and footprints stay unchanged for millions of years. A mark made by an astronaut today might still be visible thousands of years in the future. Interestingly, the Moon's gravity is not evenly distributed. Certain areas, especially near old impact basins, have slightly higher or lower gravitational pull. These anomalies can affect spacecraft navigation, which scientists must carefully plan for in lunar missions. Understanding lunar gravity also helps us model gravity on other celestial bodies, like Mars or the moons of Jupiter. It's a key part of planning future exploration, construction, and long-term human presence beyond Earth. Every environment has its own gravitational rules. Even though it's weaker, lunar gravity is still strong enough to keep the Moon spherical. influence the Earth's tides and affect space travel. It may not pull as hard as Earth does, but it still shapes the Moon's identity and our future in space. How the Moon influences Earth's tides and climate. It's easy to think of the Moon as a distant object, silently floating in space. But in reality, it has a powerful influence on Earth, especially when it comes to tides. The ocean's rise and fall, happening twice a day around the world, is largely controlled by the Moon's gravity. As the Moon orbits Earth, its gravity pulls on the planet's oceans. This creates a bulge of water on the side facing the Moon. Interestingly, there's also a second bulge on the opposite side, caused by inertia as the Earth-Moon system rotates. These bulges move as the Moon moves, creating tides. When a coastal area rotates into one of these bulges, the tide rises. When it moves away, the tide falls. That's why most places experience 2 high tides and 2 low tides each day. The Sun also contributes to tides, but the Moon has a stronger effect because it's closer to Earth. During full moons and new moons, the Earth, Moon, and Sun align. This alignment causes spring tides, higher highs, and lower lows. When the Moon is at first or last quarter, the forces partially cancel each other out, leading to neap tides, which are milder. Tides do more than just move water. They affect marine life, influence fishing, shape coastlines, and even help circulate heat in the oceans. Over long periods, they can impact climate patterns by redistributing energy across the planet. But does the Moon affect Earth's climate directly? Not in the same way the Sun does, but there are subtle influences. Tidal mixing helps regulate ocean temperatures and the flow of nutrients. Some studies suggest this process has a stabilizing effect on long-term climate trends. The Moon also helps keep Earth's axial tilt stable. Without the Moon's gravitational pull, Earth's tilt could vary wildly over time. This tilt is what causes our seasons, so keeping it steady helps maintain a relatively stable climate over thousands of years. If the Moon didn't exist, Earth's rotation might slow down more dramatically. The Moon acts like a brake, using tidal friction to gradually slow our spin. As a result, days are getting longer by about 1.7 milliseconds per century. This tiny effect adds up over geological time. In fact, when dinosaurs roamed the Earth, days were only about 23 hours long. Go back even further, and the days were shorter still. The Moon's influence has been shaping Earth's rhythm for billions of years, a kind of silent partner in the evolution of life. Without the Moon, Earth might have more extreme climate swings, less predictable seasons, and a more chaotic rotation. Its presence adds a stabilizing force that's hard to overstate. It's not just a light in the night sky, it's a balancing act for life. Understanding the Moon's role in tides and climate helps us see how interconnected everything is. Oceans, gravity, the tilt of our planet, they all work together in a dynamic system. The Moon may seem distant, but its fingerprints are everywhere on Earth. From gentle ocean waves to the length of our days, the Moon quietly shapes our planet's behavior. Its gravitational pull is constant and powerful, a reminder that even distant objects can have profound effects on life here. Blood moons and lunar eclipses explained. A blood moon sounds dramatic, and it looks even more so. The Moon turns a deep reddish color, almost like it's glowing with fire. It's one of the most striking sights in the night sky. But what causes this eerie transformation? The answer lies in the Earth's shadow. A blood moon happens during a total lunar eclipse. This occurs when the Earth moves directly between the Sun and the Moon, casting its shadow on the lunar surface. You'd think the Moon would go completely dark, but instead it glows red. Why? The reason has to do with how Earth's atmosphere bends light. When sunlight passes through our atmosphere, shorter wavelengths, like blue and green, scatter in all directions. That's why the sky is blue. But longer wavelengths, like red and orange, pass through and bend around Earth. This bent red light is what reaches the moon during a total eclipse. It paints the surface with a rusty glow. In a way, you're seeing all the sunrises and sunsets on Earth at once, projected onto the moon. It's a breathtaking coincidence of geometry and light physics. Not every eclipse produces a deep red moon. The color depends on how much dust, smoke, or pollution is in Earth's atmosphere. A volcanic eruption, for example, can make the moon appear even darker or bloodier than usual. In some eclipses, the moon can even look gray or copper. Lunar eclipses don't happen every full moon. That's because the moon's orbit is tilted about 5 degrees relative to Earth's orbit around the sun. Most of the time, the moon passes slightly above or below Earth's shadow. Eclipses only occur when everything aligns just right. There are 3 main types of lunar eclipses: penumbral, partial, and total. In a penumbral eclipse, the moon just grazes the outer shadow and dims slightly. In a partial eclipse, only part of the moon enters the dark shadow. A total eclipse is the most dramatic, with the full blood-red effect. One great thing about lunar eclipses is that they're safe to watch with the naked eye. Unlike solar eclipses, there's no danger in looking directly at them. They also last longer, sometimes up to an hour, giving people plenty of time to watch and reflect on what they're seeing. Cultures around the world have interpreted blood moons in different ways. Some saw them as omens or signs from the gods. Others used them to mark time or predict events. Today, we understand the science, but the awe remains because the visual impact is just as powerful. Blood moons are also predictable. Astronomers can forecast them hundreds of years in advance. They follow precise cycles, like the Saros cycle, which repeats eclipses roughly every 18 years. Even ancient civilizations tracked these patterns long before modern science. Watching a lunar eclipse is like watching the mechanics of the solar system in real time. The sun, earth, and moon align perfectly, a moment of cosmic choreography. And for a little while, the moon becomes a glowing ember in the night sky. What seems like a mystical event is actually a simple play of light, shadow, and motion. But that's part of the beauty of science. It reveals the truth behind the wonder and shows that nature doesn't need magic to be amazing. Lunar regolith, the dust that destroys equipment. The moon might look smooth from far away, but up close, its surface is covered with something dangerous: regolith. This is the fine, powdery dust that coats the entire moon. It's not just any dust. It's sharp, clingy, and destructive. And it causes big problems for both humans and machines. Regolith forms over billions of years as micrometeorites crash into the moon. With no atmosphere to burn them up, every small impact hits the surface directly. These impacts shatter rocks into tiny, jagged particles. The result is a layer of dust unlike anything on Earth. The dust is incredibly fine, almost like flour, but it's also razor sharp. That's because there's no weather or water on the moon to smooth the edges. Each particle keeps its sharpness, making it abrasive to anything it touches. For astronauts and equipment, it's a serious hazard. During the Apollo missions, astronauts found that regolith stuck to everything: suits, tools, visors, and even skin. It clung like static and was nearly impossible to brush off. Inside the lunar module, it got into electronics and caused annoying, even dangerous issues. The jagged dust scratched visors and damaged joints in the astronauts' suits. They reported smelling a burnt gunpowder scent after returning to the module, likely from regolith particles reacting with oxygen. NASA quickly realized this wasn't just dirt, it was a serious technical problem. Regolith is also electrostatically charged by solar radiation. That means it can float slightly above the surface and cling to anything nearby. Over time, it can work its way into hinges, seals, and instruments, degrading performance or even causing failure. Because the Moon has no atmosphere, there's nothing to trap or move the dust. It just stays where it lands, permanently. Every step, every landing, and every rover stirs it up again. It's like walking through dry ashes that never settle or wash away. Modern lunar missions have to take regolith into account during every stage of planning. Engineers design rovers and landers with extra seals, shields, and protections. Future moon bases will need systems to limit how much dust enters living quarters or machinery. Scientists are also studying how to use regolith as a resource. It might be possible to melt it into bricks for construction, or to extract oxygen from its minerals. But handling it safely will always be a challenge, especially if humans are going to live and work on the Moon long term. Some robotic missions are testing ways to minimize dust disturbances, like gentle landings and dust-repelling surfaces, but nothing fully solves the issue yet. Regolith remains one of the biggest technical obstacles to sustained lunar exploration. Understanding lunar dust isn't just about safety. It also tells us about the Moon's history. The thickness and composition of the regolith record billions of years of impacts, space weathering, and solar activity. It's like a dusty library of the solar system. So even though it looks like harmless gray powder, lunar regolith is one of the most hostile substances in space exploration. To return to the Moon and stay there, we'll need to solve the problem of the dust that never stops clinging. Why days on Earth are getting longer? Because of the Moon. Did you know Earth's days used to be shorter? A long time ago, one full rotation took only about 18 hours. Today, it's just over 24 hours, and it's still getting longer. What's causing this slow change? The surprising answer is the Moon. As the Moon orbits Earth, its gravity pulls on our planet. That pull causes ocean tides, but it also creates a kind of drag. The energy from Earth's rotation transfers to the Moon, causing Earth to slow down very gradually over time. This process is called tidal friction. It happens because Earth's rotation causes the tidal bulge to be slightly ahead of the Moon. The Moon pulls back on this bulge, creating resistance, like braking a spinning wheel. That friction robs Earth of a little rotational energy. As Earth loses rotational speed, our days stretch out just a little. We're talking about milliseconds per century. But over billions of years, it adds up. When dinosaurs were alive, a day was around 23 hours long. Go back to the early Earth, and days were even shorter. At the same time, the Moon gains energy from this exchange. That energy pushes it farther away in its orbit, very slowly. So, as Earth slows down, the Moon moves away, like a silent cosmic trade, time for distance, gravity for motion. This connection between the Earth's rotation and the Moon's orbit helps stabilize both bodies. It keeps Earth's axial tilt steady, which is important for a stable climate and consistent seasons. Without this interaction, Earth might wobble chaotically. We know all this thanks to geology and astronomy. By studying ancient rocks with tidal markings like ripple patterns and fossil layers, scientists can calculate the length of a day millions of years ago. These natural records confirm what physics predicts. This slowing doesn't affect daily life much, but it's a reminder that our world is constantly changing. The passage of time itself is influenced by the Moon, literally. Clocks may be precise, but planetary time is always on the move. Some scientists believe the moon helped create the conditions for life by slowing Earth's spin. A more stable rotation means less extreme weather, predictable light cycles, and better environmental consistency. Life thrives on rhythm, and the moon helped set the tempo. Eventually, in the very distant future, Earth's rotation could become synchronized with the moon. That would mean Earth always shows the same face to the moon, just like the moon does now. But this would take tens of billions of years, longer than the sun will even last. Understanding how the moon affects Earth's rotation helps us grasp the deep connections in our solar system. Even distant objects interact in powerful, invisible ways. Gravity is always at work, shaping time, space, and the rhythms of our lives. So the next time you check the time, remember, your 24-hour day exists because of a slow cosmic dance with the moon. It's not just a light in the sky, it's part of what makes life on Earth the way it is. The moon's gradual drift away from Earth. It might sound hard to believe, but the moon is slowly moving away from us, a little more each year. Right now, the moon drifts about 3.8 centimeters farther from Earth every year. It's a tiny shift, but over time, it adds up. This movement is linked to the same tidal forces that slow Earth's rotation. As Earth's spin transfers energy to the moon, it pushes the moon into a higher orbit. It's like giving the moon a gentle nudge outward, again and again over millions of years. We've measured this with incredible accuracy thanks to retro-reflectors left by Apollo missions. These are mirrors that bounce back laser beams sent from Earth. By timing how long the light takes to return, scientists can calculate the moon's distance, down to the millimeter. When the moon formed, it was much closer, maybe only 22,000 kilometers away. Now, it's over 384,000 kilometers from us. That increasing gap changes many things: tides, Earth's rotation, and the way eclipses happen. The farther the moon gets, the more those effects evolve. As the moon moves away, Earth's tides are getting slightly weaker. With less gravitational pull, the tidal bulges become less dramatic. Over time, this could affect ocean life and coastal systems. But the change is extremely slow, so it's not a current threat. Another big impact: eclipses. In the far future, total solar eclipses may no longer be possible. The moon will appear smaller in the sky and won't fully block the sun. Only partial or annular eclipses will occur. We live in a rare period when total eclipses are still possible. This outward drift is part of a long-term trend, but it won't go on forever. Eventually, Earth and Moon could reach a state called tidal locking, where both bodies always show the same face to each other. But that will take more time than the age of the universe so far. Some ancient legends and stories imagined the moon falling from the sky. But in reality, the opposite is happening. It's escaping, very slowly. Not fast enough to notice in a lifetime, but significant over geological time. The moon's gradual departure also changes how we think about the history of the Earth-Moon system. It suggests that the early Earth experienced much stronger tides, faster rotation, and a different balance of forces than we see today. These subtle shifts remind us that nothing in space is static. Orbits change, distances stretch, and forces continue acting even when we don't notice. The moon is quietly changing its relationship with Earth, and always has been. It's also a lesson in precision. That we can measure a few centimeters of motion over hundreds of thousands of kilometers is a triumph of science. And it shows how interconnected motion, gravity, and time are across space. The moon may look like it's standing still in the sky, but it's always on the move. Even in silence, it's pulling away, centimeter by centimeter, changing the Earth in ways we can measure, study, and understand.
Did the moon ever have active volcanoes? When we think of volcanoes, we usually picture Earth, lava pouring from mountains, smoke filling the sky. But what about the moon? Surprisingly, yes, the moon used to have volcanoes. They were active billions of years ago, and their effects are still visible today. The moon's volcanic activity was very different from Earth's. There weren't towering cones or explosive eruptions. Instead, most of the volcanism was calm and slow, producing massive flows of lava that spread across low areas. These flows formed the dark regions we see today. This volcanic period peaked around 3 to 4 billion years ago. Back then, the moon's interior was still hot enough to melt rock. That heat came from leftover energy after its formation and the decay of radioactive elements. But over time, the moon's interior cooled and hardened. Unlike Earth, the moon lacks plate tectonics. That means volcanic activity wasn't caused by moving plates, but by internal pressure and cracks in the crust. Lava would rise through these cracks and spread across the surface, often filling in impact basins created by asteroids. The lava was basaltic, a dense, dark rock also found in places like Hawaii. This explains the moon's color contrast. The dark areas are solidified lava flows, while the brighter highlands are older, untouched crust. These dark zones are now known as lunar maria. The moon's last major volcanic eruptions likely happened around 1 to 2 billion years ago, but some signs suggest small eruptions may have occurred more recently, maybe even 100 million years ago. That's still ancient, but much younger than once thought. How do we know this? Astronomers study the shape and composition of surface features. Smooth plains, collapsed lava tubes, and wrinkle ridges all point to a volcanic past. Plus, rocks brought back from the moon contain minerals that only form from molten lava. No active volcanoes exist on the moon today, and it's unlikely that they'll return. The moon's core is mostly solid now, and its internal heat is too weak to drive eruptions. It has become a geologically quiet world, cold, still, and silent. That said, the moon might still have thermal activity deep inside. Instruments left by Apollo missions detected minor moonquakes, signs of internal motion. These aren't volcanic, but they show that the moon isn't completely frozen on the inside. Volcanism helped shape the moon's surface and history. Without it, the Maria wouldn't exist. Those dark patches we see from Earth are the fossilized footprints of ancient lava flows, reminders of a time when the moon was far more dynamic. Understanding lunar volcanism also teaches us about other worlds. Mars, Venus, and even some moons of Jupiter have volcanic histories. By studying the moon, we learn more about how planetary bodies evolve over time, even the quiet ones. The huge dark plains called Maria. When you look at the moon with your eyes, or even through a telescope, you'll notice large dark patches scattered across its surface. These are called Maria, Latin for seas, and they give the moon its familiar man-in-the-moon look. But they're not oceans, they're ancient lava plains. The Maria were formed billions of years ago when massive asteroids slammed into the moon's surface. These impacts created huge basins, breaking open the crust. Later, lava from the moon's interior rose up through the cracks and filled these basins, creating vast, flat plains.
Unlike the Moon's highlands, which are bright and heavily cratered, the Maria are darker and smoother. The difference comes from their composition. The lava that created the Maria is rich in iron and magnesium, which gives it a darker tone compared to the silicate-rich highlands. Most Maria are on the near side of the Moon, the side that faces Earth. That's because the Moon's crust is thinner on that side, making it easier for lava to reach the surface. The far side, with its thicker crust, has far fewer Maria and remains more cratered. The largest Maria include Mare Imbrium, Mare Serenitatis, and Mare Tranquillitatis, where Apollo 11 landed. Some of these Maria are over 1,000 kilometers wide, covering huge portions of the Moon. They're among the most recognizable features in the solar system. Despite the name, there's no water in the Maria. Ancient astronomers thought they might be seas, hence the name, but we now know they're dry as dust. Still, the name stuck, and it gives the Moon a poetic edge, seas of stone, frozen in silence. The Maria aren't completely flat. They contain features like wrinkle ridges, caused when the lava cooled and contracted, and small hills formed by later impacts. But compared to the rugged highlands, they appear almost calm, like a frozen ocean. These lava plains preserve important information about the Moon's past. By dating rocks from the Maria, scientists can trace the timing of volcanic activity and major impacts. Some Maria are among the youngest large features on the Moon, only 1 to 2 billion years old. The smoothness of the Maria also made them ideal for early Moon landings. NASA chose these flat, predictable regions for Apollo missions because they offered safer terrain for landing and walking. That's why so many human footprints are found on ancient lava. From Earth, the Maria formed familiar shapes: a smiling face, a rabbit, a person. Every culture has seen something different in the Moon's markings. But beyond mythology, they tell a real story of fire, force, and cooling over billions of years. Studying the Maria helps us understand planetary resurfacing. Similar lava plains exist on Mars and Mercury. By comparing them, we can learn how planets heal their wounds, turning violent impacts into flat, dark scars. The Maria may look quiet and still, but they're records of deep violence and fiery recovery. They remind us that even in silence, the Moon carries the memory of ancient destruction and slow, molten rebirth. Extreme temperatures between lunar day and night. The Moon has no atmosphere, and that changes everything. One of the biggest effects? Wild temperature swings between day and night. While Earth's atmosphere helps regulate heat, the Moon's lack of one means temperatures can rise and fall dramatically in just a few hours. During the lunar day, temperatures can reach up to 127 degrees Celsius, or 260 degrees Fahrenheit. That's hotter than boiling water, enough to damage equipment and scorch any unprotected surface. The sun shines directly on the Moon's surface for about 14 Earth days at a time. Then, when the sun sets, the temperature plunges. During the lunar night, it can drop to minus 173 degrees Celsius or minus 280 degrees Fahrenheit. That's colder than any place on Earth. With no atmosphere to trap heat, all warmth radiates into space almost instantly. This makes the Moon one of the most thermally extreme places we've studied up close. The same spot can swing over 300 degrees Celsius in temperature from day to night. For future Moon missions, this presents major engineering challenges. Spacecraft, rovers, and habitats need to be insulated against both freezing cold and intense heat. Apollo astronauts only stayed during the early lunar morning, when temperatures were more moderate. Longer missions will require high-tech thermal control systems. The temperature also varies depending on where you are. Near the poles, where the sun stays low on the horizon, conditions are more stable.
In permanently shadowed craters, temperatures never rise above freezing and often drop to record lows. These cold traps are interesting because they may contain frozen water. Sunlight never reaches them, so ice brought by comets or formed chemically can remain preserved for billions of years. That's why lunar poles are prime targets for future exploration. On the other hand, areas near the equator experience the most extreme shifts. Sunlight hits directly, cooking the surface during the day, then leaves it frozen at night. There's no gradual transition, just full heat or full cold. The surface itself doesn't help much. The lunar soil, or regolith, doesn't hold heat well. It warms quickly when the sun rises and cools just as fast when it sets. That means even a few centimeters below the surface, temperatures are much more stable. Understanding these temperature swings is essential for planning moon bases. Everything, from power systems to life support, must handle these extremes. Heating during the night, cooling during the day, and storing energy through the long darkness all require innovation. Temperature sensors placed by Apollo missions have helped scientists model heat flow on the moon. These models inform today's rover designs and tomorrow's habitats. Every mission adds new data about how to survive on a world with no air and no mercy. The moon looks calm, but its environment is one of the harshest in the solar system. From scorching heat to deadly cold, it's a place where every sunrise and sunset transforms the surface and tests the limits of what life and machines can endure. Permanently shadowed regions on the moon's poles. Near the moon's poles, some craters are so deep and the sun stays so low in the sky that sunlight never reaches their interiors. These are known as permanently shadowed regions, or PSRs. They're among the coldest places in the entire solar system. Because the moon has almost no axial tilt, only about 1.5 degrees, the sun's rays hit the poles at a very shallow angle. That means the floors of deep craters near the poles remain in constant darkness, even as the moon rotates. Without sunlight, there's no heat. These regions can reach temperatures as low as minus 240 degrees Celsius or minus 400 degrees Fahrenheit. That's colder than Pluto. In these deep freeze zones, nothing melts or evaporates. They act like natural deep space refrigerators. These shadowed areas exist mainly in the South Pole and to a lesser extent at the North Pole. Some have been in darkness for over 2 billion years, completely untouched by light or heat. They are like time capsules from the early solar system. What makes them so important is what they might contain. Scientists believe these regions trap and preserve water ice, delivered by comets or formed through chemical reactions over billions of years. That ice could be a game changer for future missions. Mapping these regions is difficult. They're in total darkness, so normal imaging doesn't work. Instead, scientists use radar, laser altimeters, and infrared sensors to see inside them. Recent missions like NASA's LRO and India's Chandrayaan-1 have revealed their shapes and depths. Some of these PSRs are enormous. The crater Shackleton, near the South Pole, is more than 20 kilometers wide and has a rim that receives near-constant sunlight, while the interior stays forever dark. It's one of the top targets for exploration. Landing in or near these regions is a major engineering challenge. Spacecraft need to navigate extreme darkness and cold and survive in conditions that no mission has faced before. But the rewards, access to ancient ice and unique geology, are worth the risk. PSRs might also serve as natural storage areas. Future lunar bases could use them to keep equipment cool, store volatile substances, or build protected scientific stations. The cold itself becomes a useful tool if we can learn to live with it.
Because these areas haven't been exposed to solar radiation or temperature swings, they may contain pristine materials from early in the Moon's history. Analyzing them could help scientists understand how the Moon, and maybe Earth, formed and evolved. Some scientists believe these regions are the best places to search for signs of past organic chemistry. Not life, but building blocks, frozen and preserved through time. It's one of the few places in the inner solar system where ancient organics might survive intact. Permanently shadowed regions are among the Moon's most mysterious and valuable features. Dark, cold, and silent, they hold secrets buried in time and could be the key to making life on the Moon possible in the future. The presence of frozen water in shadowed craters. For decades, scientists debated whether water could exist on the Moon. Now we know the answer: yes, in the form of ice. And much of it is hidden inside the Moon's permanently shadowed craters, especially near the South Pole. These dark craters never see sunlight, so temperatures are low enough to preserve water molecules that would otherwise evaporate. Some of this water was likely delivered by comets, which slammed into the Moon billions of years ago. Other sources may include solar wind interacting with oxygen in the lunar soil to form hydroxyl, a chemical cousin of water. Over time, these processes built up tiny amounts of ice, molecule by molecule, slowly accumulating in the coldest, darkest places. NASA's ELSI mission confirmed the presence of water in 2009. The spacecraft crashed into a shadowed crater and analyzed the material thrown into space. What it found was unmistakable: ice particles mixed with dust, proving that frozen water really is there. Later missions and radar observations showed that hundreds of craters might contain surface or buried ice. Some of it may be pure enough to extract and use, while other areas might have just traces. It's not oceans, but it's enough to matter. Water is critical for any long-term lunar mission, not just for drinking, but for making oxygen and hydrogen, which could support life and fuel rockets. A base near the poles could use this ice to create a self-sustaining outpost. Extracting the ice won't be easy. It's mixed with soil and frozen solid, often hidden beneath rock. Tools would need to dig, drill, and heat the material to release usable water. Still, the potential payoff is enormous. It means less material would need to be brought from Earth. This discovery also raises big questions. How old is the ice? Has it been there for millions or billions of years? If so, it could hold chemical traces of the early solar system, a frozen record of time hidden in lunar darkness. Even small amounts of water can change everything. It reduces the cost and complexity of space travel. With enough ice, the Moon could become a refueling station for deeper missions, like a launch pad for Mars or beyond. Some researchers think there might also be frost on the sunlit surface. Not enough to harvest, but enough to prove that water is more widespread than we thought. It shows the Moon is not as dry or lifeless as once believed. This changes how we think about the Moon entirely. Once seen as a barren desert, it's now seen as a resource-rich body with potential for habitats, industry, and science. Water turns a lifeless rock into a stepping stone for humanity. Finding water on the Moon isn't just a scientific win, it's a practical one. It opens doors to exploration, sustainability, and survival. And it all starts in the shadows, where ancient ice quietly waits. The Moon's strange and localized magnetic field. Unlike Earth, the Moon has no global magnetic field today, but that wasn't always the case. Long ago, the Moon had a magnetic field, and even now, strange, localized magnetic patches still exist across its surface, puzzling scientists. Earth's magnetic field is generated by movement in its liquid iron core. The Moon also has an iron core, but it's much smaller and mostly solid. That's why it lost its global magnetic field billions of years ago. It simply cooled down too much. However, rocks collected during Apollo missions show that parts of the Moon were once magnetized. This suggests that for hundreds of millions of years, the Moon had a weak but real magnetic field, enough to leave traces in volcanic rock as it cooled. Even more curious are the local magnetic anomalies still found on the Moon. These are small areas, often just a few hundred kilometers wide, where magnetic fields are stronger than anywhere else. They don't line up with the Moon's poles or any known pattern. One famous example is the Reiner Gamma Formation, a bright, swirling pattern on the Moon's surface, paired with a strong magnetic field. No one fully understands what created it. Some theories say it could be from ancient magnetic rock or even comet impacts. These magnetic patches might still protect small areas from solar radiation. Unlike Earth's global magnetosphere, which shields the entire planet, these lunar zones could offer micro-protection. That could matter for future landers or equipment. The Moon's magnetic field may have originated from early core convection, when its interior was hotter and more active. As it cooled, the field gradually faded. The leftover magnetized rocks are like ancient fossils of that magnetic era. Recent studies suggest impacts might also play a role. When an asteroid hits, the heat and pressure can magnetize rock, especially if the Moon had even a weak magnetic field at the time. This might explain why some magnetic patches are near old impact basins. Learning about these anomalies helps scientists understand how planetary magnetic fields form and fade. It also gives clues about the Moon's interior, its cooling process, and its geological evolution over billions of years. For space missions, these magnetic regions could interfere with instruments or offer clues about where to explore next. Some proposals even suggest studying them up close to search for rare magnetic minerals or preserved solar wind particles. Compared to Earth's magnetic shield, the Moon's field is faint and fractured, but even in fragments, it tells a rich story, one of heat, motion, and time. The Moon may no longer have a magnetic heart, but it still carries magnetic memories in its crust. So while the Moon seems cold and quiet now, its surface still hums with invisible fields, strange, isolated echoes of a once lively interior, and reminders that even in silence, a world can hold secrets. The mysterious holes called lava tubes. Across the Moon's surface, scientists have discovered strange, deep pits, some with smooth walls and perfectly round shapes. These aren't just craters. They're believed to be collapsed skylights of ancient lava tubes, tunnels formed billions of years ago by flowing magma. Lava tubes form when molten lava flows beneath a hardened surface. As the outer layer cools, it creates a crust, while lava continues to move through the center. When the flow stops and drains out, it leaves behind an empty tunnel, a lava tube. On Earth, lava tubes are found in places like Hawaii and Iceland. But on the Moon, they could be much larger, wide enough to fit entire cities. That's because of lower gravity and no erosion. Some tubes may be hundreds of meters wide and stretch for kilometers underground. NASA and other space agencies have identified dozens of potential entrances to these lava tubes. They appear as deep, round holes in the surface, sometimes over 100 meters wide and 50 meters deep. These are called pit craters or skylights. Why do they matter? Lava tubes could be perfect shelters for future lunar missions. Inside, temperatures are stable, and walls would protect against radiation, micrometeorites, and dust. They're like ready-made bunkers carved by nature. On the Moon's surface, temperatures swing wildly. from plus 127 degrees Celsius to minus 173 degrees Celsius. That's cold, but manageable. For astronauts, this kind of environment could offer a much more survivable home base. Some proposals suggest building entire lunar colonies inside lava tubes. We wouldn't need to build massive surface structures, just seal parts of the tunnel and use them for living, labs, or storage. That could save time, money, and materials. Scientists are eager to explore them, but getting inside is tricky. Rovers would need to descend steep drops, navigate dark tunnels, and survive without direct sunlight. Missions like Japan's Selene and NASA's Artemis program have included them in their long-term goals. These tubes might also preserve ancient material. Because they're sealed off from the surface, they could contain untouched regolith, or even chemical traces from billions of years ago. They may act as archives of the Moon's volcanic past. Even more exciting, some researchers believe similar lava tubes exist on Mars. Studying them on the Moon could prepare us for using them on other planets, where surface radiation is even more dangerous. The idea of astronauts living underground might sound like science fiction, but in space, natural protection is rare. Lava tubes offer something incredibly valuable: a stable, shielded environment, ready for human exploration. From mysterious pits to possible habitats, lava tubes are one of the Moon's most fascinating features. Beneath the silence of the lunar surface, there may be vast tunnels, dark, ancient, and waiting to be explored. Apollo 11 and the first human step on the Moon. On July 20, 1969, history changed forever. For the first time, humans set foot on another world. The Apollo 11 mission, led by NASA, brought astronauts Neil Armstrong and Buzz Aldrin to the surface of the Moon, while Michael Collins orbited above. It wasn't just a technical achievement, it was a moment of global unity. Over 600 million people watched as Armstrong stepped onto the Moon and said the now famous words, "That's one small step for man, one giant leap for mankind." The mission launched from Florida aboard a Saturn V rocket, still the most powerful rocket ever used. After reaching lunar orbit, Armstrong and Aldrin descended in the lunar module Eagle, leaving Collins in the command module Columbia. Landing wasn't easy. The autopilot aimed for a field of boulders, so Armstrong took manual control and landed with just seconds of fuel left. When they finally touched down, Armstrong calmly reported, "The Eagle has landed." They spent only 2.5 hours outside, collecting samples, setting up instruments, and placing an American flag. One key experiment was the laser retroreflector, which scientists still use today to measure the distance to the Moon. Armstrong and Aldrin brought back 21.5 kilograms of rocks and soil, which revolutionized our understanding of the Moon's composition. These samples showed that the Moon is made of basaltic rock formed from ancient lava flows. Meanwhile, Michael Collins remained in orbit, circling the Moon alone. He later said he never felt lonely, only deeply aware of how far from Earth they really were and how fragile our world looked from space. Apollo 11 was more than a flag-planting mission. It proved that human exploration beyond Earth was possible. It opened doors to science, technology, and imagination. 6 more Apollo missions followed, but Apollo 11 remains the first. The landing site, Tranquility Base, is now a historic site. The flag they planted is probably bleached by sunlight, but the footprints? Still there. With no wind or rain, they may last for millions of years. They left behind more than footprints. They also left instruments, tools, the descent stage of the lander, and even personal items. Buzz Aldrin left a small memorial for fallen astronauts and cosmonauts, a silent tribute on alien soil. It took over 400,000 people working in science, math, engineering, and logistics to make Apollo 11 happen. It was a human achievement on a scale never seen before and never forgotten. Apollo 11 reminded us that exploration is part of who we are. One step on the moon changed how we see our place in the universe, and it proved that, given enough effort, even the impossible can become real.
How we measure the moon's distance with lasers. You might wonder, how do we know exactly how far away the moon is? The answer involves one of the cleverest and most precise tools in space science: lasers. Since 1969, we've been bouncing laser beams off the moon to measure its distance with millimeter precision. During the Apollo 11, 14, and 15 missions, astronauts placed retroreflectors on the moon. These are arrays of tiny glass prisms that reflect light directly back to its source, no matter the angle. It's like a cosmic mirror designed for extreme precision. Back on Earth, observatories fire powerful laser pulses toward the moon. These beams travel the 384,000 kilometers to the retroreflector, bounce off it, and return to Earth. By timing how long the round trip takes, we can calculate the distance. Light travels at a known speed, about 299,792 kilometers per second. So, if it takes 2.5 seconds for the beam to go and return, the moon is about 384,000 kilometers away. The actual measurements are much more detailed, accounting for atmosphere, signal loss, and equipment calibration. This system is called lunar laser ranging. It's been running for over 50 years and has produced a treasure trove of data, not just about distance, but also about how the moon's orbit is changing over time. Thanks to these measurements, we know that the moon is slowly drifting away from Earth, about 3.8 centimeters per year. It also helps confirm theories about gravitational physics, including aspects of Einstein's general relativity. The lasers used are incredibly precise. Despite spreading out to several kilometers wide by the time they reach the moon, a few photons still bounce back and are detected. It's a test of patience, engineering, and exact science. Only a few places on Earth can do this kind of work, including observatories in Texas, France, and Hawaii. The signals are weak, but the data is powerful. It shows us the real-time motion of a celestial body hundreds of thousands of kilometers away. The retroreflectors are still working today, even after decades in the harsh lunar environment. They have no power source, no moving parts, just clever engineering sitting silently in the dust, waiting for the next beam of light. Future missions may install new reflectors, possibly at the lunar poles or far side. These would give us better data on the moon's shape, rotation, and internal structure, and keep the laser experiments going for generations. Measuring the moon's distance isn't just about numbers, it's about tracking the heartbeat of the Earth-Moon system. Every laser pulse is a question: where are you now? And every reflection is an answer, sent back from the edge of space. It's a quiet, elegant method, proof that even with our advanced technology, sometimes the best way to understand the universe is with a flash of light and a long wait. The human objects left behind on the moon. When astronauts visited the moon, they didn't take everything back with them. In fact, they left over 200 tons of human-made objects scattered across the lunar surface. From high-tech instruments to personal items, the moon is now home to a strange collection of space history. Some of these objects are scientific tools: seismometers, retroreflectors, and magnetometers, placed to study the moon's surface and interior. Others are pieces of equipment too heavy or unnecessary to bring home, like lander descent stages, backpacks, and cameras. Every Apollo mission left behind their landing platform,
also known as the Lunar Module Descent Stage. These still sit silently at each landing site, their golden foil faded by decades of solar radiation, untouched since the day they landed. But not everything is technical. Apollo 11 left a plaque that reads, "We came in peace for all mankind." Other missions left family photographs, medals, flags, and mission patches. Buzz Aldrin even left a small aluminum sculpture honoring fallen astronauts and cosmonauts. The astronauts also left footprints, which are still there today. With no wind, rain, or erosion, those prints may last for millions of years. They're a permanent record of humanity's first steps on another world. There are also some unusual items, like golf balls hit by Alan Shepard during Apollo 14, and a falcon feather dropped during a gravity experiment. There's even bags of human waste left behind to reduce weight for the return trip. Scientific packages like the ALU-SEP, Apollo Lunar Surface Experiments Package, continued collecting data long after the astronauts left. Some of these transmitted information back to Earth for years, offering priceless insight into lunar conditions. Beyond the Apollo missions, robotic landers from the Soviet Union, China, and the United States have all left hardware on the Moon. This includes landers, rovers, crash stages, and impact probes, all now part of the Moon's growing museum. In total, over 70 human artifacts from at least 18 missions are spread across the surface. Most of them are concentrated in specific regions, like the lunar equator, where conditions were ideal for landing. Some people worry about lunar littering, but for now, these objects are considered part of human heritage. Several organizations, including NASA, want to protect the landing sites as historical landmarks for future explorers. In the years to come, we may return to these sites. Future astronauts could visit Tranquility Base, stand beside the same flag planted in 1969, or examine the descent stage still resting in the dust. These aren't just objects, they're milestones of human achievement. What we've left on the Moon tells a story of science, adventure, and humanity reaching beyond Earth. They are reminders that we were there and that we can go back. The Moon as Earth's shield against asteroids. When you look at the Moon's surface, you see a landscape scarred by craters. Each one is the result of an impact, some small, some massive. But those craters tell another story, how the Moon has protected Earth from countless collisions over billions of years. The Moon acts like a natural shield, intercepting space debris that might otherwise hit Earth. It doesn't attract objects like a magnet, but its position and size mean that it sometimes takes the hit, absorbing impacts that could have been catastrophic here. This role is especially important during heavy bombardment periods, like the one 4 billion years ago when the inner solar system was filled with asteroids. During this time, both Earth and the Moon were targets, but Earth's geological activity erased many of its craters, while the Moon kept the scars. Some large craters on the Moon, like Imbrium, Serenitatis, and South Pole Aitken, were created by impacts powerful enough to destroy regions of Earth. But thanks to the Moon, some of that energy never reached us. The Moon doesn't block all impacts. Earth is much bigger and still gets hit. We've seen that with events like the Chicxulub asteroid, which likely led to the extinction of the dinosaurs. But statistically, the Moon has reduced the number of direct hits on Earth over time. It also helps us study impact history. Because its surface is preserved, the Moon acts like a record keeper of collisions. By counting and dating lunar craters, scientists estimate how often large impacts occur and predict future risks for Earth. The Moon's stabilizing effect on Earth's axial tilt also plays a protective role. By keeping our climate more predictable, it reduces chaotic swings that could disrupt ecosystems or human civilization. It's not just a shield in space, but a buffer in time. The moon can't stop everything, but its presence definitely matters. It creates a gravitational influence that slightly alters the paths of objects passing near Earth. Sometimes that's enough to shift an asteroid away from a collision course. If Earth had no moon, life here might have faced more frequent and destructive impacts. Some scientists believe life might have struggled to gain a foothold under constant threat. In that sense, the moon didn't just protect us, it helped us survive. Some researchers have proposed using the moon as an early warning station for tracking near-Earth objects. Telescopes or radar arrays on its far side could scan the sky 24/7 without interference from Earth's atmosphere. In the future, understanding how the moon has taken hits for us might help us design better defense systems. By studying its cratered surface, we learn how to prepare for future threats and build technologies to protect Earth more actively. So while the moon looks peaceful in the sky, it's been a silent guardian for billions of years, absorbing impacts, preserving history, and helping life on Earth thrive. The psychological and cultural impact of the moon. The moon has shaped human imagination for as long as we've looked up at the night sky. Unlike stars, it changes shape, moves quickly, and lights the sky with a glow that feels almost alive. Its presence has left a deep mark on our culture, language, and emotions. Ancient civilizations built calendars around its phases. From the Babylonians to the Mayans, the moon served as a natural timekeeper, tracking months, tides, and seasons. Even today, words like month come from the word moon. The moon has been a symbol of fertility, madness, love, and transformation. Its changing phases inspired myths of werewolves, lunar gods, and dreamlike creatures. Many cultures link the moon to feminine energy and cycles of nature. In literature and art, the moon appears as a companion to solitude, romance, or mystery. Poets and painters across centuries used it as a metaphor for longing, distance, or inspiration. Even now, a full moon in a movie scene often signals something magical or strange. Psychologically, the moon affects us in subtle ways. Some studies suggest full moons might slightly influence sleep, mood, or behavior, though results are mixed. The belief in lunar madness, or lunacy, is ancient, but its scientific basis is still debated. Many people feel a special connection to the moon. It's close enough to see detail, yet far enough to feel unreachable. That balance gives it a unique place in the human mind, a symbol of mystery, rhythm, and stability all at once. Religious and spiritual traditions often center around the moon. From Islamic lunar calendars to Hindu festivals and Wiccan rituals, its phases are used to mark sacred time. It bridges the physical and the symbolic in ways few other objects do. The moon also played a role in human ambition. It was the first goal of space exploration and the first place humans walked beyond Earth. That accomplishment changed how we see ourselves, not just as Earthlings, but as part of the cosmic story. Even children draw the moon instinctively, a crescent in the sky, a smiling face. It's embedded in human memory, passed down across generations. No other celestial object is so intimately connected to daily life and imagination. In modern times, the moon continues to inspire. Musicians write songs about it, artists paint it, and scientists plan missions to return. It's both ancient and futuristic, a bridge between our past myths and our future frontiers. The moon doesn't just reflect sunlight. It reflects human emotion,
curiosity and wonder. Its pull is more than gravitational. It's deeply psychological, shaping how we dream, believe, and explore. Across cultures, ages, and disciplines, the moon stands as a shared symbol, whether guiding calendars, inspiring stories, or pulling ocean tides. It remains a constant, always above us, always changing, always inviting us to look up. Alternative theories about the moon's origin. The leading theory says the moon formed after a giant impact between Earth and a Mars-sized body. But that's not the only idea scientists have considered. Over the years, several alternative theories have been proposed to explain the moon's mysterious beginnings. One of the earliest theories was the fission theory. It suggested that the moon split off from a fast-spinning molten Earth. The idea was that a chunk of Earth's outer layer tore away and formed the moon, possibly explaining why their compositions are similar. Another theory was capture. It claimed the moon formed elsewhere in the solar system and was later pulled into Earth's orbit by gravity. While that sounds plausible, it doesn't explain the moon's stable orbit or its similar isotopic makeup compared to Earth. There was also the co-formation theory, where Earth and the moon formed side by side in the same region of space. But this would likely lead to very different chemical compositions between the two, and the moon's lower iron content doesn't fit that model. Each theory had strengths and weaknesses, but none explained all the evidence. The giant impact theory became dominant because it fits both the physical and chemical data, the moon's size, orbit, composition, and lack of a large core. However, even the impact theory has challenges. Some scientists point out that isotope ratios in moon rocks are too similar to Earth's. If a lot of the moon came from another planet, we'd expect more variation. That led to modified impact models. One version says the impact completely vaporized both Earth's and Thea's outer layers, mixing the material into a shared disk. From that, the moon condensed, explaining the chemical similarity. Others suggest Earth and Thea were made of nearly identical material to begin with. There's also a newer hypothesis called the synestia model. In this version, the collision created a huge spinning cloud of vaporized rock, a donut-shaped structure called a synestia. The moon formed inside this hot, turbulent ring before it cooled. Outside mainstream science, some more exotic ideas exist, like the moon being a captured dwarf planet or even artificial in origin. While these are not supported by evidence, they reflect how much fascination the moon inspires. The truth is, we're still refining the details. Missions like Artemis and robotic sample returns may help settle debates by giving us new types of lunar material, especially from the far side or deep below the surface. Understanding the moon's origin isn't just about the moon. It also helps explain how Earth formed, how planets grow, and how collisions shape solar systems. It's a key piece in the puzzle of planetary science. While the giant impact theory remains the best supported explanation, alternative ideas remind us that science is always evolving. The moon's story isn't fully written, and with every discovery, we get closer to understanding its ancient birth. The possibility of mining helium-3 on the moon. Among the many resources the moon might offer, one stands out as especially futuristic: helium-3. This rare isotope has been called the fuel of tomorrow, a potential energy source for clean nuclear fusion, and the moon may have plenty of it. Helium-3 is a variant of helium with 2 protons and 1 neutron. On Earth, it's incredibly rare. We produce only small amounts in labs. But on the moon, it's been accumulating in the soil for billions of years, delivered by the solar wind.
The Moon doesn't have a magnetic field or thick atmosphere, so particles from the Sun, including helium-3, hit its surface directly and embed into the regolith, the layer of lunar dust and rock. Over time, this has built up measurable quantities. Estimates vary, but some suggest there could be up to 1 million metric tons of helium-3 on the Moon. That's enough, in theory, to power all Earth's energy needs for centuries, if fusion reactors capable of using it were developed. Unlike current nuclear power, helium-3 fusion doesn't produce dangerous radioactive waste or high neutron radiation. It's clean, efficient, and safe, at least in theory. The problem is, we haven't built a working reactor that can use it yet. Even if we could build the reactors, mining helium-3 on the Moon would be a huge challenge. It's found in very low concentrations, around 10 to 20 parts per billion in lunar soil. That means you'd need to process tons of material to extract small amounts. The process would involve heating the regolith to around 600 degrees Celsius to release the helium-3 gas. Then it would need to be stored, shipped back to Earth, and integrated into a working energy infrastructure. It's a long-term, high-cost project. Still, some countries, including China and the United States, have shown interest. China's Chang'e missions have mapped areas rich in helium-3, and future plans may include experimental mining or sampling of high-potential zones. Supporters say it's worth investing in now to prepare for a future where clean fusion power is vital. Critics argue that building reliable fusion reactors on Earth should come first, before investing in lunar mining. Even if helium-3 isn't used for energy anytime soon, learning to extract it could have other benefits. It would help us develop automated mining systems, test new technologies for resource extraction, and lay the groundwork for space-based industry. Mining helium-3 might not solve today's energy problems, but it represents a vision for the future, one where the Moon becomes not just a destination, but a supplier of clean power for Earth. It's bold, complex, and full of potential. What it would be like to live in a lunar colony. Living on the Moon sounds like science fiction, but it may happen sooner than we think. With new missions planned and permanent bases in development, the idea of a lunar colony is becoming more realistic. But what would daily life there actually be like? The first challenge is shelter. Moon bases would need to protect people from radiation, micrometeorites, and extreme temperatures. Most designs propose building habitats underground, inside lava tubes, or using thick regolith to insulate the structures. Air, water, and food would be tightly controlled. Life support systems would recycle everything, including air and waste. Water could come from ice at the lunar poles, while food might be grown in hydroponic systems powered by sunlight or nuclear energy. Astronauts would wear special suits to go outside. The lunar surface has no atmosphere, and temperatures can swing over 300 degrees Celsius between day and night. Each excursion, or EVA, would be carefully timed, planned, and monitored from mission control. Gravity is only 1/6 that of Earth, so daily movement would feel different. Walking becomes hopping, and heavy objects become easier to lift. But over time, low gravity can cause muscle and bone loss, so colonists would need regular exercise routines. Energy would come from solar panels, especially near the poles where some areas receive nearly constant sunlight. Backup systems, like nuclear power, would ensure that life continues during long lunar nights, which last about 14 Earth days. Communication would be nearly real-time, with only about a 1.3-second delay. That's good enough for video calls and live updates with Earth. Still, colonists would need to be highly self-sufficient, solving problems with limited help. Mental health would be a major concern. The moon is isolated, quiet, and emotionally intense. Crew members would likely live in close quarters, with little privacy. Regular contact with loved ones, entertainment, and purposeful work would be essential. There would also be opportunities for science and exploration. Colonists could study lunar geology, test new materials, and experiment with long-term survival in space. It would be like living in a permanent research station, but on another world. Over time, bases might grow into mini-cities, with 3D printed buildings, greenhouses, and even factories. They could serve as hubs for tourism, industry, or staging areas for deeper space missions, especially to Mars. Daily life would involve routine, maintenance, research, physical training, and constant system checks. Emergencies, like equipment failure or air leaks, would require quick, calm responses. Safety training would be a way of life. Living on the moon wouldn't be easy, but it would be meaningful. Every action would be part of something larger, the human expansion into space. A lunar colony would be the first real step toward becoming a multi-planetary species. For now, it's a vision, but with each new mission, that vision gets closer, and someday soon, waking up on the moon might be just another morning in humanity's next chapter. The invisible dangers of radiation on the moon. The moon may look peaceful, but its surface is one of the most dangerous places for humans. One of the biggest threats? Radiation. Unlike Earth, the moon has no atmosphere or magnetic field to shield it from space radiation, and that creates serious risks. On Earth, we're protected by the magnetosphere, which deflects harmful solar and cosmic particles. The moon, however, is fully exposed. That means astronauts on the lunar surface face high doses of radiation from the sun and deep space. There are two main types of radiation to worry about: solar particle events, like solar flares, and galactic cosmic rays. Solar flares can blast the moon with intense bursts of particles in minutes. Cosmic rays are constant and come from distant stars and galaxies. Even during calm space weather, radiation on the moon is much higher than on Earth. A short mission might be safe, but long-term exposure can damage cells, increase cancer risk, and weaken the immune system. It's not something you can feel, but it's always there. The Apollo missions avoided this problem by keeping astronauts on the moon for only a few days and during periods of low solar activity. But future missions aiming for longer stays or permanent bases need to take radiation protection seriously. Shielding is the main defense. This could include thick walls of regolith, water tanks, or even underground shelters. Natural features like lava tubes could offer protection by blocking radiation with meters of rock. Spacesuits and spacecraft offer only limited shielding, especially against cosmic rays. Engineers are working on new materials that might better protect astronauts without adding too much weight, a constant trade-off in space design. Another strategy is monitoring the sun. Space agencies track solar activity in real time. If a dangerous solar flare is coming, astronauts could take cover in a storm shelter, a heavily shielded part of their habitat or rover. Radiation can also affect electronics and equipment, not just humans. It can disrupt data, damage sensors, and shorten the lifespan of robotic systems. That's why lunar tech must be hardened against these invisible, high-energy threats. Understanding radiation exposure is also essential for missions to Mars and beyond. The moon acts as a test bed, a place to learn how to live and work in deep space where Earth's protection can't reach. Some researchers are even exploring biological countermeasures like special diets, drugs, or gene therapies to protect cells from radiation damage. It's early-stage science, but could one day help humans thrive in high-radiation environments. Radiation may be invisible, but it's one of the biggest barriers to permanent lunar life. Solving it is key to turning the moon from a short visit into a long-term home and opening the door to deeper human space exploration. Does time pass differently on the moon? Relativity and gravity. Does time move the same on the moon as it does on Earth? The answer is not exactly. Thanks to Einstein's theory of relativity, time is affected by gravity and motion. And since the moon has different gravity than Earth, that means time does pass slightly differently there. According to general relativity, time flows more slowly in stronger gravitational fields. Earth's gravity is stronger than the moon's, so time on the moon ticks a little faster than on Earth. Not by much, but it's measurable. The difference is about 58 microseconds per day. That means in one Earth day, a clock on the moon would run 58 microseconds ahead. Over a year, that adds up to around 21 milliseconds. Still tiny, but enough to matter for precision systems. These effects are already considered in GPS satellites, which orbit Earth at high altitudes. Their clocks also tick slightly faster than those on the ground. Engineers constantly correct for these differences to keep systems accurate. On the moon, future lunar colonies will need to do the same. Timekeeping for navigation, communication, and science must be carefully synced with Earth, especially when controlling rovers or sending signals between the two worlds. There's also special relativity, which says that the faster you move, the slower your time flows. On the moon, that effect is minimal because people and machines won't be moving fast enough to notice. But for spacecraft, it does become relevant. Time dilation has been confirmed by experiments many times. Atomic clocks flown on airplanes and satellites experience tiny shifts compared to those on the ground. The moon simply adds another setting where these laws apply. NASA and the European Space Agency are working on lunar time standards, a way to create a unified clock system for the moon based on these relativistic differences. That will be essential for future missions and lunar navigation networks. For astronauts, these time shifts won't be noticeable. They'll still live by schedules, alarms, and mission timelines. But for scientists and systems, every microsecond counts, especially when coordinating operations between Earth and Moon. The concept also invites deeper thought. Time isn't absolute. It flows differently depending on where you are and how you move. What feels normal to us on Earth is just one version of how the universe measures time. The Moon may be close, but even there, the clock ticks just a little bit differently. Relativity isn't just a theory. It's something we must live with, plan for, and understand as we expand into space. So yes, time on the Moon moves faster than on Earth. Not by much, but enough to remind us that even something as familiar as a second depends on where you are in the cosmos. The Moon around other planets and why ours is unique. Moons are common in the solar system. Every planet beyond Mercury and Venus has at least one, and some have dozens. Jupiter and Saturn have more than 80 each. But Earth's moon is unlike any other, and its uniqueness has fascinated scientists for decades. Most moons are tiny compared to their planets, but Earth's moon is unusually large. It's about 1/4 the diameter of Earth and 1/81st of its mass, a massive ratio for a planet-moon system. That makes it the largest moon relative to its host planet. This size gives the moon unusual power. It stabilizes Earth's tilt,
affects tides, and may have helped make Earth's climate stable enough for life. No other moon in the solar system plays such a dramatic role in the fate of its host planet. Most large moons, like Ganymede, Titan, and Callisto, formed with their planets or were captured later. But Earth's moon likely formed from a giant impact, making its history more violent and more directly connected to our planet. Many moons around other planets are icy, with subsurface oceans. Europa and Enceladus, for example, may host conditions for life. Earth's moon, by contrast, is dry, rocky, and airless, but close, familiar, and deeply tied to human history. The moon also offers an ideal platform for science. Unlike the moons of gas giants, it's only 3 days away. It's a place we can visit, build on, and use to test life beyond Earth, something no other moon can offer in the short term. Because of its size and gravity, the moon affects Earth in ways other moons don't. Imagine if Earth had no moon. Our rotation might wobble wildly, tides would shrink, and long-term climate stability could be lost. Life here could be very different. Some planets have multiple moons. Mars has 2 small ones, Phobos and Deimos. They're irregular, like captured asteroids, and too tiny to have much effect. Our moon, by comparison, is spherical, massive, and formed through a completely different process. The moon has also become a cultural symbol, something rare among other moons. No one writes poems about Titan or sings about Phobos. Earth's moon is part of human language, myth, and art. It has shaped our identity in ways no other satellite has. It's also the only moon where humans have walked. That alone makes it stand out. While other moons may host alien oceans or secrets beneath their ice, only one has boot prints, flags, and a human history written in the dust. As we explore the solar system, we'll study many more moons, but none will ever play the same role as ours. Earth's moon isn't just a satellite, it's a partner in our planet's story, and a gateway to the rest of the cosmos. In a universe full of moons, Earth's remains strangely and beautifully unique, not just because of what it is, but because of what it means to us. The moon's influence on biological and hormonal cycles. For centuries, people have believed the moon affects human behavior and biology. Full moons have been linked to sleep problems, mood swings, and even crime rates. But is there real science behind these ideas, or is it just myth? Many natural rhythms are tied to the lunar cycle. The most obvious is the ocean tides. But some animals also time behaviors, like mating or migration, to phases of the moon. Coral spawning, for example, often happens during full moons. Some marine species, insects, and birds use the moon's light for orientation. The lunar cycle also affects the nocturnal visibility of prey and predators, altering feeding habits in many ecosystems. In nature, the moon is a reliable cosmic clock. But what about humans? Some studies suggest sleep quality decreases slightly during a full moon, even in dark rooms. People may fall asleep later, sleep less deeply, or wake up more during the night, possibly due to ancient evolutionary responses to nighttime light. However, results vary between individuals and cultures. Not all studies agree, and the effects are usually small. Researchers are still exploring whether these patterns are consistent enough to be considered biological or just statistical noise. There's also interest in whether the moon influences hormonal cycles, especially in women. The menstrual cycle averages around 29.5 days, the same length as the lunar month. Some believe this is more than coincidence, but science hasn't reached a clear conclusion. While some people naturally sync with the moon, others don't. Urban environments with artificial light may override any lunar connection. Still, the overlap in cycle length has sparked debate and cultural traditions for thousands of years.
In ancient cultures, the moon was often linked to fertility, growth, and health. Farmers used moon phases to guide planting. Some calendars were entirely lunar. These traditions reflect how closely people once lived in tune with lunar rhythms. In modern life, the moon's direct biological influence is likely small, but not zero. Our circadian rhythms are shaped more by sunlight, but there may still be subtle lunar effects, especially on sleep and melatonin production. Psychologically, the moon can have a strong effect. Its phases are visible and emotionally charged. People may expect changes during full moons, leading to self-fulfilling shifts in mood or behavior. Belief can drive perception. The moon remains a symbol of cycles, change, and time. Whether it truly shifts our hormones or sleep isn't fully settled, but it clearly resonates with something deep in our biology and culture, connecting us to natural rhythms that stretch across time. In the end, even if its pull on the body is small, the moon's presence continues to shape our awareness, rituals, and rhythms, and that's a kind of influence all its own. Why the moon looks much larger when it's low in the sky, near the horizon. It can seem massive, almost unnaturally so, compared to when it's high overhead. This effect is striking, but it's not caused by actual size change. In reality, the moon's size in the sky stays almost exactly the same throughout the night. The distance between Earth and Moon doesn't change much hour to hour, so why does it look so much bigger near the horizon? This is known as the moon illusion, and it's one of the oldest optical illusions known to humans. For thousands of years, people have noticed it and tried to explain it. But the effect happens entirely in the brain, not in the sky. One major factor is visual context. When the moon is near the horizon, your brain compares it to trees, buildings, or hills. These familiar reference points make the moon appear larger than when it's floating alone in a blank sky. When the moon is higher up, there's no frame of reference, just empty space. Without nearby objects for comparison, your brain perceives it as smaller. It's the same moon, same size, same distance, just a different visual environment. Some scientists suggest that our brains treat the sky like a flattened dome. Things on the horizon seem farther away, so if the moon appears large and far, the brain interprets it as physically larger than usual to make sense of the scene. You can test this illusion yourself. Try holding a coin at arm's length when the moon is on the horizon, then again when it's overhead. You'll see it covers the same amount of moon both times, even though your perception is totally different. Photography confirms this too. A camera captures the moon at the same size regardless of its position in the sky, unless you use a telephoto lens, which artificially magnifies it. So the effect is 100% in your perception, not the moon itself. This illusion isn't unique to the moon. The sun also looks bigger when rising or setting, for the same reasons. But the moon draws more attention because it appears against the dark sky, more dramatic, more mystical. Interestingly, people often associate a large moon with emotional or spiritual experiences. The illusion amplifies our response. It feels more powerful, closer, or significant. It's a perfect example of how perception can shape emotion. So next time you see a massive moon on the horizon, remember, it hasn't grown. Your brain is playing a trick, a beautiful one, rooted in millions of years of evolution. The moon didn't change, you did. And sometimes that's what makes it feel so magical. The possibility of moonquakes. The moon may seem like a silent, motionless world, but it's not completely still. Beneath its surface, the Moon experiences seismic activity, known as moonquakes. These events are real, and they offer clues about the Moon's internal structure and evolution. During the Apollo missions, astronauts placed seismometers on the Moon to measure ground motion. These instruments recorded thousands of moonquakes over several years, proving that the lunar crust is not entirely dead. There are four main types of moonquakes: deep moonquakes, shallow moonquakes, thermal quakes, and those caused by meteorite impacts. Each type comes from a different source, some natural, some environmental. Deep moonquakes happen about 700 to 1,200 kilometers below the surface. They occur in regular patterns, likely triggered by tidal forces from Earth's gravity. They're relatively weak, but show the Moon's interior still responds to external stress. Shallow moonquakes are more concerning. These occur closer to the surface and can be surprisingly strong, reaching magnitudes of 5 on the Richter scale. That's enough to crack rock and potentially damage lunar structures. Then there are thermal moonquakes, which happen when the Moon's surface rapidly heats up at sunrise. The expansion and contraction of the crust causes minor shifts, like the Moon creaking as it warms and cools. Lastly, there are quakes caused by meteorite impacts. With no atmosphere, even small objects hit the Moon hard, generating shock waves. These are sudden and unpredictable, unlike the more regular tidal or thermal quakes. Moonquakes are different from earthquakes. They last much longer, sometimes up to 10 minutes, because the Moon's crust is more rigid and dry. On Earth, water and softer rock help absorb seismic waves. On the Moon, they just bounce around. Understanding moonquakes is vital for building lunar habitats. Future bases must be designed to withstand both natural tremors and shock from impacts. Engineers study these patterns to choose safer locations for landers and stations. Studying moonquakes also reveals what lies beneath the surface. The way seismic waves travel tell us about the Moon's crust, mantle, and core. It's like sonar for planetary science, giving us a map of what we can't see. So even if the Moon seems still, it isn't. It flexes, shifts, and reacts. Quietly, slowly, but constantly. Moonquakes remind us that the Moon is not a frozen rock, but a dynamic world with a story still unfolding beneath its dusty surface.
The future of the Moon in missions to Mars. To reach Mars, we might first need to return to the Moon, not just to visit, but to build, test, and launch from it. The Moon is no longer just a destination. It's becoming a staging ground for the next phase of human space exploration. Launching from Earth to Mars takes enormous fuel, resources, and coordination. But the Moon has much lower gravity, just 1/6 that of Earth. That means launching from the Moon requires far less energy, making it an ideal site for interplanetary missions. NASA's Artemis program plans to establish a sustainable lunar base, including Gateway, a small space station that will orbit the Moon. This station will serve as a stopover for astronauts heading to the lunar surface, and eventually Mars. Before going to Mars, we need to master long-term survival in space. The Moon is close enough to practice that safely. A lunar base will test life support systems, resource extraction, construction, and autonomous operations, all necessary for Mars. One of the most important capabilities is in situ resource utilization, ISRU, using local materials instead of bringing everything from Earth. On the Moon, that could mean extracting water from ice, making fuel from lunar soil, or building with regolith-based bricks. These technologies could then be adapted for Mars, where similar challenges exist. If we can prove them on the Moon, we'll be far more prepared for the 8-month journey and surface operations on Mars, where help from Earth is limited.
There's also psychological value. Lunar missions can simulate isolation, confinement, and distance, helping researchers understand how astronauts will handle months in space away from Earth. The Moon becomes a rehearsal, not just technically, but emotionally. The Moon may also serve as a fuel depot. If we can produce liquid hydrogen and oxygen from lunar ice, we could refuel deep space missions more cheaply. A Mars-bound rocket could launch from Earth light, refuel in lunar orbit, and then continue outward. Some proposals even suggest assembling spacecraft in lunar orbit using parts launched separately. The lunar's low gravity and lack of atmosphere make it easier to manage large, complex assemblies in space. International cooperation is key. The Moon provides a shared goal where agencies like NASA, ESA, Roscosmos, CNSA, and private companies can test interoperability, robotics, AI systems, and policy frameworks for deep space governance. By making the Moon our first outpost, we lay the groundwork for becoming an interplanetary species. It's the bridge between low Earth orbit and the vast unknown. A permanent human presence on the Moon would be our most ambitious milestone yet, until Mars. The road to Mars begins on the Moon, not just symbolically, but practically. And what we build there, stations, systems, habits, may someday be mirrored across the solar system. The Moon as an eternal archive of solar system history. The Moon isn't just a satellite, it's a cosmic time capsule. Because it has no atmosphere, no erosion, and minimal geological activity, the Moon has preserved billions of years of solar system history in its surface. It's one of the best archives we have. On Earth, wind, water, and plate tectonics erase or bury ancient evidence. But the Moon's surface has barely changed in billions of years. Every crater, layer of dust, and rock fragment is a page in the story of our cosmic neighborhood. Meteorites that hit the Moon are preserved where they landed. Their impact sites stay sharp and readable. Some craters on the Moon are over 4 billion years old, giving us a glimpse into the violent early days of the inner solar system. The Moon's regolith, or surface dust, is full of preserved solar wind particles, micrometeorites, and cosmic rays. This layer acts like a record of space weather, solar activity, and even galactic events that Earth's environment has long since erased. Some areas of the Moon might even preserve interstellar particles or ancient fragments from Theia, the planet-sized body thought to have collided with Earth to form the Moon. These could hold clues to the materials that built the planets. The far side of the Moon, especially inside deep craters, is a particularly undisturbed archive. It hasn't been exposed to Earth's magnetic field or artificial interference. Scientists dream of drilling into these areas to retrieve pristine samples from deep time. Rocks brought back by the Apollo missions have already revealed massive events, like the Late Heavy Bombardment, a period when many planets were pummeled by asteroids. Earth's record of this is mostly lost. The Moon keeps it all intact. Some researchers believe the Moon could even hold fossilized molecules or organics delivered by ancient comets or meteorites. While there's no evidence of life, the Moon might contain the chemical building blocks that seeded early Earth. Because of this stability, some propose using the Moon as a backup for Earth's data, a place to store digital archives in hardened memory banks away from war, weather, or cyber attacks. The Moon could become humanity's library in space. Future lunar missions may involve deep core drilling, sample returns from unexplored regions, or radar scans of underground structures. Each mission would add more pages to our understanding of planetary formation and evolution. Unlike Mars, where weather and dust storms shape the surface, the Moon preserves nearly everything.
It is slow-moving time, frozen in rock and dust. It doesn't just reflect the past, it holds it. Studying the moon is like reading the oldest, most complete diary of our solar system. And as long as it remains untouched, it will continue to be the most faithful witness to everything that has ever happened in the skies around us.